we saw, for example, in Witten's paper, that if we had, say, a meson that we could think as a quark and an anti-quark, I remind you, that was the picture for the meson in the large N paper of Witten. And then, when this guy starts interacting, it starts exchanging gluons between the quark and anti-quark, right? And we said that the diagrams that are planar, these diagrams here, that are planar, dominate over non-planar diagrams, and you end up with kind of a picture like this, where you have a bunch of gluon interactions between these quarks and antiquarks, and you have all these gluons that you have to sum over, and that describe the interactions between these quarks and antiquarks. And as we discussed, as we said, if I am in the large N limit, planar stuff dominates, and so we end up here with many vertices, but planar. In other words, we get with some kind of discretization of a surface. Right? So this looks like some kind of surface. More precisely, this looks like the surface of an open string. Right? So it looks like the quark is an endpoint of the string, the anti-quark is the other endpoint. So we have a quark, we have an anti-quark, and there is a string that stretches between the quark and the anti-quark. And as the quark and anti-quark move in time, as they move in time, this string will swap a surface, and it will draw a surface, and this surface would be this surface of the string. And so we have this picture of a string between a quark and an anti-quark, and that string, if you do QCD, you would call this string also the flux tube. A tube of energy that connects the quark and the anti-quark. Right? And if you did simulations in QCD, for example, you would really see this tube of energy between the quark and the anti-quark. Okay, so far so good, no puzzle. But now let's think of this picture. Take this picture in a gauge theory that is a conformal field theory. Namely, a theory without scale. A bit like electromagnetism, free electromagnetism. Then if you do it, you don't get this flux tube of energy. This is not what you get. Instead, what you get, if you have a conformal theory, is that the force between the quark and the anti-quark decays as 1 over the radius, like Coulomb force. That's the only thing that can be. And why does it decay? Because the line of forces of the chromodynamic gauge field open up, and if you draw these lines, there would be something like this, totally different from these squeezed lines that connect 2 points. That would be the correct picture between the quark and an anti-quark in a CFT, and if they are separated by r, this would give me some Coulomb potential alpha over r, and this would be the Faraday lines. And this would be, if you want, toothed flux tube. So we have this puzzle. Who is right? Is it toothed or Faraday? What's the picture? Do I have a flux tube between the two, as this large N diagrams indicate, some surface? Or do I have Faraday lines and they are totally delocalized and I get 1 over r? Which is correct? Right, so here I have some quark and some anti-quark, and the potential between the quark and the anti-quark would be alpha over r.
But you mean some CFT, but where does the CFT come from?
I'm saying there is a CFT which has gluons, there are many, n equals 4 supreme Mills is one example,
Okay.
but there are many such theories. You can take QED. QED is just U1, the force decays as 1 over r, but it's not special to being U1, it's special to not having a scale. If you don't have a scale, the potential is 1 over r. So potential being 1 over r is not at all like a flux tube. It's the opposite. It's delocalized, right? It's like Coulomb force or gravitational force. It's everything but a tube. There's nothing in the tube. It's like spherical 1 over r. And on the other hand, we do have these planar graphs that resemble very much a string between the quark and the anti-quark. And if there is a string between the two, I imagine it as some tube, some flux tube of energy that pulls them apart. So what's wrong? Is there no string picture? Should I drop the string picture and the flux tube? Or should I drop Faraday even if I am in a CFT? No. For this argument, no, it will not make a difference. If it's in higher dimensions, the potential will be 1 over r to some power. The Faraday lines would still be like this. It will still decay.
Even in 2 dimensions is 1 over r?
No, in 2 dimensions, no. But if it's more than 3 dimensions, it is like this. So let's suppose we are in 4 dimensions, 5 dimensions, 6 dimensions. We have this puzzle. Okay? So it's a small puzzle. Of course, some of you know the answer to this puzzle. Don't spoil it. But it's an interesting puzzle, so this would be a puzzle. At least I see it as a small puzzle of this tension or tension between this picture of tooth, that there should be a string, and this picture of Faraday that says there's no flux tube, it's rather totally delocalized. Okay? And we'll come to the answer of this puzzle at the very end of the lecture. Okay, so that's one thing I wanted to do before we start. The second thing is to remind you of something basic about effective field theory, which is that gravity is not, we were not lucky to have gravity. Gravity is the unique thing we could have. So as soon as you tell me that I have a theory where the degrees of freedom are some metric plus some perturbation, and I have some diffeomorphism invariance, then this automatically implies that my action is gravity. Why? Because I write everything I can write, and reach is the thing with the smallest number of derivatives. And so it's what dominates at low energy. Right? So it's not like we need to come up to think a lot and so on. Now we know in modern terms that once you know the degrees of freedom, you write everything that you can that's compatible with those degrees of freedom. The things with the smallest dimensions dominate, and higher dimensions are subleading in the infrared. Right? So we know immediately it's GR. Does it mean it's exactly GR? No. Then we start getting corrections, like R squared with some coefficient. But these corrections are suppressed in the infrared. They don't matter in the infrared, they are suppressed. And as soon as I tell you this, you immediately derive that you have Coulomb force, that you have gravity waves, and so on. That all follows because there's nothing more it could be. Right? You could also have, if you had a gauge field, similarly, you would also write some F squared, and again, there would be some corrections times some F to the 4 plus, etc. And these irrelevant operators would start showing up when I start cranking up the energy, but at low energy, it's F squared and that's it. It's not like I need to tune or do anything. And of course, they could also couple. I could also write some kind of R mu nu, F mu nu, etc. And again, they are there. They exist, but they are subleading at low energy. Okay? So this describes the massless relevant degrees of freedom in the infrared. particular, in string theory, we have two things. We have closed strings and we have open strings, like the open strings I drew there. And these separate further. When you zoom out, they look like point particles, but they separate further into massless strings and massive stuff, massless strings and massive stuff. And if I go to low energy, I keep only the massless stuff, first of all. Right? No one cares about massive stuff, that decays exponential. So not only I keep the massless stuff, not only I keep the massless stuff only, but, so we keep m equals 0, and we keep the leading IFT that describes this massless degrees of freedom. That would be the analog of saying, for example, closed strings. It includes, for example, the graviton as a closed string, and the gluon as the open string. And when I take low energy, not only I keep only gravitons and gluons and massless states, but also I only keep R. I don't keep R squared, R cubed, etc. That's not relevant for low energy, like it never is. Okay? So this is just some basic stuff so that we are on the same page. And one more thing is that closed strings, we already saw some in the Gross-Mendel paper, right? We said that we have some sphere with a bunch of punctures and so on. Open string is similar, except that the open string, it's not a map from a circle to the target space, it's a map from a segment to the target space. But you see that it has endpoints. And so in string theory, we need to specify where are these endpoints. For example, I could postulate, I could decide that I have some open strings in this room that can end, the endpoints can be anywhere in the room. That's one option. The other option is no, the endpoints are stuck to the blackboard. And that's another option. Now they live in 2 dimensions. Before they lived in 3 dimensions. And so endpoints that could be moving in the room, they would be able to move in 3 dimensions plus time. So if these endpoints are in the room, they would be in what we call a D3 brane. Because it moves in 3 dimensions plus time. And so it moves on an object that's like a plane but in 3D. So this is a 3D brane. If the endpoints would be stuck to the blackboard, then it's a 2-dimensional object plus time, so it would be a D2 brane, etc. And so string theory, on top of strings, it has these objects that can be planes, D1s, D2s, D3s, D4s, which are dimension D plus 1 objects where the open strings end. Okay? And we are going to use this object, these planes, these D3 branes, we are going to use them today. Okay. So let's start. And what we want to do today is do a low energy limit. So what we want to do is look at a system and look at it at low energy. And we will see that doing this thought experiment of preparing a system and looking at it at low energy will give rise to a duality. There will be 2 ways of thinking of the same system. And these 2 different ways of thinking about the system will give a duality, and that's ADS-CFT. Good. I think it's useful, yeah, this lecture probably is going to be a little bit longer because I'm giving a little bit too much background, but I think maybe it's useful. I think it's useful to think of the following toy example for thinking about the system in two different ways. Suppose I have an electron that is passing by a proton. So I have a proton. A proton is a very heavy object. So that's a proton. Right? Proton is basically infinite mass, right? Very heavy. And then we have an electron that passes by this proton. And I want to study its deflection by the proton. How do I study this deflection by the proton? One way of studying is by doing all possible Feynman graphs that interact between the proton and the photon. Well, maybe the leading one, just one exchange. Just one exchange would give Coulomb force and would tell me that the potential would be something like some Q over R. But then I start correcting and I start finding some Bremsstrahlung corrections and some radiative corrections to the potential due to the graphs. And I start finding corrections to this Newton's force. I start finding, I don't know, some correction of the form, some exponential corrections, for example, some corrections to the force with some particular coefficients, plus etc. Right? And this would come from starting to correct these diagrams with electron loops and photon vertices and so on and so forth. So this would be one description. I have the proton, and this I would call this, that I have the, so this would be like the Feynman diagram side, where I have an electron in flat space, and the electron exchanges stuff with some line that's the proton. The other option is to say, I have my electron, and the proton generates a background for the electron. The effect of the electron interacting with the proton is to effectively, I replace the proton, I remove it, and replace it by some non-trivial background. And now there is a background V of R, and there is no proton. I just say that someone managed to compute everything, and by computing everything you found the potential V of R. And now I ignore the proton. What I'm not going to do is compute the potential and then leave the proton there and do more diagrams. That will be too much. So either I say there's no potential, there's only diagrams, and I compute diagrams, more and more and more and more and more. Or I say there's no proton at all, but there is a potential. So I have these two ways of thinking, the background, or there is no background, if you want V is equal to 0, but there are all these interactions. So I either have V equals 0 with lots of interactions, or I have no proton, but there is an untrivial potential where it moves. And this Feynman diagram side equal to potential side would be like a toy model for what we are going to do. This would be like ADS, and this would be like CFT. I think this is a good analogy for ADS-CFT. So we will see this would be like the analog of CFT, and this would be the analog of ADS. How do I compute the full potential? On lattice, using lattice QCD, for example. Or developing an expansion where I expand not at small parameter but at some large parameter, doing some reverse expansion. Or maybe I don't compute it, I guess it. And then I try to guess with a bunch of free parameters, and I match those free parameters so that the computations here and here work. And when those computations are working, now I make new predictions and I check if they work. There are many strategies I could use. But you are right that it could be that I might be able to control one side much better than the other. And sometimes knowing that the two are equivalent it's not yet very useful unless I have a clean dictionary between how do I compute something in this case, like some deflection angle, and something in this case, like a sum of Feynman diagram. And that's the same in ADS-CFT. Just saying n equals 4 is equal to string theory, like this is a bit useless. I need to supplement it with a very sharp dictionary saying you compute this in the CFT and you compute that in gravity. And same thing here. And same thing with any duality. Okay, so now we want to do this, exactly this, in string theory. The proton, what do you think we could replace the proton by? Someone want to get some non-string theorist that read the Mauthausen's paper? So we want to replace the proton, our very heavy object, by something very heavy in string theory. What of the object I spoke about, which ones are very heavy? Not the open and closed strings. Those are very tiny loops. They are very light. What was the other object I spoke about in string theory? Brain. Okay? So instead of proton, we will put a D-brain. But actually, to make it really heavy, we will not put one, we will put a stack of them, many of them, like a deck of cards. Okay? So that's the fundamental starting point. Instead of proton, we'll put this, which is a stack, which just means they are on top of each other, a stack of many n D3 brains. Okay. And then I ask, what is the low energy limit of this? Right? So what is it? What's the low energy limit of this? I remind you, string theory lives in 10 dimensions. So here, there are 3 plus 1 dimensions. So here, there are 6 dimensions that are flying around. In the same way that when I put the brain in the blackboard, there will be 1 dimension extra here. In string theory, there are 6 extra ones here. Okay, now I have this. So universe is empty in 10 dimensions, except there is a tabletop which has a bunch of stack of D-brains. What are the low energy degrees of freedom here that matter? What matters at low energy? Based on what I said before. Sorry? Gravity. Exactly. So here we could have some gravitons. So this would be gravity. It's supersymmetric, so it will be supergravity. There will be the gravitons and a bunch of other fields that are massless, but gravity basically. Good, so that's true. For example, some massive string mode that we don't care, but the gravitons we do care. What else? Gauge fields, and the gauge field would be here, localized on the brain. So here, as Rodrigo said, we would have gauge theory. Because it's open strings. Open strings need to end on the brain. So that's the only place they could end. So the same way that gravitons are small loops, open strings are small segments and they need to end on the brain. So they need to be here. This doesn't exist. Doesn't make sense. The open strings need to end on a brain by definition. And the only thing the universe has is D3 brains in this toy example we are thinking about. So there is no D9 brain. A D9 brain is also called a space-filling brain. Then the strings could end anywhere, but here there's no D9, there's only D3s. So we have these small open strings. These are the gluons. This is the graviton. And this would be the gluon. And in the same way that here we have gravity, here we have gauge theory, but here it's supergravity, and here it would also be super gauge theory. Then when we have the gluon, we have everything that is related to supersymmetry, because superstring theory doesn't come just with a particle, comes with other particles that are related to supersymmetry. What is the effective action that describes these two things? It is gravity plus Young-Mills, separated. That's why people do condensed matter, because gravity is irrelevant when you have a table. When you have a table, things live on the table, and there are low energy degrees of freedom on the table, and no one cares about gravity. Right? Why? Because gravity coupling with F is subleading. It's an irrelevant operator, like before. And so the low energy degrees of freedom is supergravity plus the gauge theory that lives on those D3 branes, which is a 4-dimensional gauge theory. Why 4-dimension? Because we decided to put D3 branes, so the degrees of freedom are on the plane. And that 4-dimensional gauge theory, with that amount of supersymmetry, is a theory that is called n equals 4 super Young-Mills, which is a CFT. It's a conformal field theory. And that describes low energy massless degrees of freedom. So this theory, if you want, is like what I wrote in the beginning, trace F squared, except that it has some fermions and some scalars, but otherwise it's like pure glue, like what we saw in other lectures. So that's what we get at low energy. It would be the same as saying it's electromagnetism plus gravity decoupled if I have a piece of material. But here it is the supersymmetric version of both, and on the table, on the D3 branes, that theory is called n equals 4 super Young-Mills.
Does the supergravity include scattering of the branes?
It could, but it will be subleading. It's an irrelevant term that couples both. But we could do that. As an experimentalist, I decide what I do. I could decide that I send the graviton and let the graviton interact with the brane and then receive it later. I could do that experiment. That is part of my low energy experiment. I can say I have the table there, I'll throw a graviton there and receive the graviton there. That is part of an experiment. We can send stuff against our table and receive it. That's what we do in experiments, right? We send an electron microscope, we bombard the table, or some neutrons, and then we see what happens. So that's part of the things we could do.
You said it's a CFT, but is it a CFT only on the low energy?
Yes, if it was not low energy enough, it would be trace F squared plus, then there would be F to the 4 plus etc. And this starts to have mass dimensions. So it would be when you flow to the infrared. Otherwise no. But when I'm saying I went to the low energy, I already dropped these terms. So what I call this super Young-Mills is already the infrared limit. It's already without this irrelevant operator. Okay? So the only thing here you would not know well, because unless you did the string theory, is about this S stuff. It's the fact that it is not just Young-Mills and it is not just gravity, it's super Young-Mills and it's super gravity. Because it comes from superstrings that has supersymmetry. So everything comes with S, and whenever you have a graviton, you have a gravitino, you have a bunch of fields that are in the same supersymmetric multiplet. Okay? That's not a big deal. Okay? So we have, this is the low energy limit of this problem in string theory. It's a Young-Mills theory plus supergravity. And we could think a little bit, okay, no, that's okay. There is a question you could ask here, but I don't want to lose time, but the question you could ask, if we have time at the end we'll go to this question, is when is this description easier to work with. / more reliable. Okay? For example, when is a Coulomb force better? When things are far away. Then it's easy and so on. Right? Then you start bringing things together, you start worrying about it. So you could ask, when is this description of the low energy degree of freedom easier to handle? Right? And let me anticipate part of the answer. When is a field theory easy? Any field theory, when is it easy? Perturbatively, right? So there is a regime where we have this gauge theory and we do just perturbation theory. That's easy. You just do one loop, 2 loops, 3 loops. Okay, 3 loops is already not easy, but okay. 1 loop, 2 loops, and you stop. No one does 3 loops. And that would be the perturbative regime. Okay. Good. But for now, okay, that's a detail. When is this easy? It's a detail. This would be true. Now, let's try to think of this, that this gauge theory is the analog of this Feynman diagram thing, because what we do in gauge theory is precisely compute all possible Feynman diagrams in my gauge theory. As Arish asked, I can even do scattering of the brains, and I send my particle, it interacts with the brain, right? I send my closed string, it interacts with the brain, it becomes an open string that propagates, and then a graviton comes out. You see the picture? There is a closed string, it becomes an open string, goes, and it comes out. Right? You see, in the middle of this open string propagating, I could draw something. I could draw a hole here, meaning that this open string would split into two. A closed string becomes an open string, the open string splits into two, joins into one, and then comes out. Right? That's the analog exactly of these processes. I have an electron coming, maybe it interacts, it splits into two, it goes, and so on. It's exactly the same thing. Moreover, not only it's exactly the same thing, but if you draw what's happening here, you are thinking that I have some probe on the gauge theory, I insert something on the gauge theory, that will be these gravitons that I scatter off the gauge theory. And then they start interacting. Right? So they start drawing something on the gauge theory, and here these are the endpoints of the string. And these endpoints go, and then apparently here they split. And then they join again, and then they end. But you recognize this, right? These are exactly the diagrams that we were drawing in the beginning, these Wheaton diagrams of the fat line rotation. So we see that these kind of fat graphs, you can think of them as literally drawing the 3D version of this is what this interaction with the brain is doing. And saying this endpoint here, the number that it could take is because there is a stack of brains. So when I draw and I say that this is an endpoint and this is an endpoint, I have to tell you this endpoint is in which of these brains. What about this endpoint? In which of them it is? So this comes with an index I, this comes with an index j. This is the index I, this is the index j. And you remember the propagator at the index ij. Then you see, if this is in brain 1 and this is in brain 7, it continues in brain 1 and 7 forever. That's what's happening here. If you go around, they stay 1 and they stay 7. But in the middle, this line here could be any of them. There is an n. Because these endpoints here, they could be in brain number 3, 4, 5, 6, 7, whatever. I have to sum over where it could be. And so this 3D picture of the interaction with the brain is really in one-to-one with these two diagrams. And when are diagrams good? When can I truncate to this? If this coupling G is small. If G is small, then the gauge theory description is awesome. I just put some probes, that would be like external gravitons that I put, for example. I let them scatter, right? And I do 1 loop, 2 loop, 3 level, okay? So I answer this question. This question is when G is small, this side is easy to work with. It doesn't mean it's not true for any G, but when G is small, it's perfect. I just do one loop diagram instead. If G starts to be bigger, I need to do more loops. I cannot start ignoring this, and I need to start drawing all diagrams. This would be like two balls on this sphere and so on. Okay. So this was this Feynman diagram side of the description. How would we think of this potential? How would we say, I don't want to think of the brains. I want to say the brain is just something very heavy. And I don't want to think this was my graviton in, graviton out. And this was all the interactions I have to sum over. I want to replace this by a picture where I have my graviton in, my graviton out, and there is some background. And I just want to say that my string moves and feels some background. And in the same way that here there is no proton, in that language there will be no D3 brains. Because I replace the effect of the D3 brains by whatever background they generate. Okay, what background does the stack of D3 brains generate? So, we go and we try to solve Einstein equation in the presence of a plane. In the same way that we solve Einstein equations in the presence of a mass and we get Schwarzschild. That's the background that a mass generates, it's Schwarzschild. Now we ask, I don't want a point particle, I want a plane. So I want to solve to find the background. I want to find this background by looking in supergravity and asking what could be the solution to the geometry. What is the metric in the presence of a stack of D3 brains generated by this stack of D3 brains? Okay, so let's do it. Let's introduce some coordinates to describe this metric. So let's say that here we have some coordinates. This could be x mu, where mu is equal 0 up to 3. These are the directions inside the brain. The 3 directions of space and 1 direction of time. And then, this would be x mu. And then there are orthogonal directions. There are 6 such directions. This would be the xm, where m takes values 5, 4, up to 9. This would be the direction orthogonal to the stack of brains. Do you agree? Okay, so what is the metric? What would be the metric? Well, by symmetry, it must be something of this form. It must be something like all these directions are the same, all these directions are the same. So it must be something of the form dxm plus something dx mu, right? Just because by symmetry the directions on the plane are the same in both ways. And what we could have is that a given point could depend on the distance to the stack of brains. That's the only thing that there could be. So there could be a function f of the distance to the stack of brain, and here another function of the distance to the stack of brain, where this r would be square root of xm. Notice that this is just a delta mm xm because these are Euclidean directions, whereas here it's eta mu nu dx mu because time is inside this part. Right? So the first time is different. Here there's no time. Here is just space. Any question here? Do you agree with this equation? That if you have a plane, things can only depend on the distance to the plane. Right? There's translation invariance here. There is a... So this would be the most general metric you could write.
But G depends
Sorry? That's the most general ansatz if you have a plane. Okay.
yeah, but this is only for one thing. You have a stack of these three.
They're on the same position. The stack is superposed. The stack are all at r equal to 0. So I put a stack of the 3 branes, they're on the same location, at r equal to 0. Yes?
So is G conditioned to be 0 at the branes means that F and G are 0 and are 0.
Say again, sorry?
That condition, that the metric is 0. At the
No, what is this 0 here? There's no 0. This is it should be a question mark.
oh,
I forgot to draw it. What's the metric? It's the question. And I'm saying it's not 0, of course. Okay, and the answer is the metric is. Okay, now what is f and g? Well, you just plug it into Einstein equation and you solve for f and g. So now you just find f and g. And you find the following result. So this is equation 2.2 of the paper. You find that g of r is equal to 1 over square root of 1 plus 4 pi g n alpha prime square, a bunch of constants. It's proportional to the charge, the number of branes, of course, and so on, divided by r to the 4. You see that this is a distance, so all this stuff here will be a distance to the power 4 as well, by dimensions. So whatever this is, let me define it, let me call it L to the 4. It's a definition of a length scale that appears. And f of r, if you solve, is 1 over g of r.
So to find this, you would need to string spectrum.
No, to find this, you now plug these ansatz into the supergravity equations of motion. The supergravity effective action, you're asking how do I derive the supergravity effective action? One way of deriving would be by comparing that action with string scattering. Then I will derive the supergravity action, and now I use that action to fix the background. Another way is to just show that the supergravity equations of motion follow from requiring that your string is a CFT.
So with the n would be what has come from.
N would come from some flux that measures how much charge is there when you measure the flux surrounded by the branes. In the same way that when you solve a Coulomb force in the vacuum, you just get that it's a constant over R. How do you fix the constant? By doing some Gauss law and checking how much charge is inside the sphere. Then you relate that constant to the charge. Here you would put some surface above and below the brane, measure how much charge there is, and then you would relate to that charge. That's the analog of M or Q. You would relate to the number of branes.
But the analogy proton and electron example would just be to do a bunch of scattering with different orders and then
Right, you would have to resum everything. Yeah. Because here at low energy, it turns out that you can resum completely this, the dynamics of the gravitons, if you will. But anyway, as long as once we accept gravity is here and we have some very heavy object, we just ask what's the solution of Einstein equations or of super Einstein equations for this simple ansatz, and this is the solution. Any question?
I need this question.
Uh-huh.
Is that like saying that writing this metric, these experiments about scattering the gravitons is embedded inside writing this metric? Is that what you're saying?
Not sure I understood that your question was exactly. So here my statement is, the D brane is a very heavy object. And so I ask, how does it back react on the geometry and find what geometry is created by a stack of D branes? The answer is this geometry. In the same way that if I say I put some very heavy point particle, what geometry will appear? It will be short-shaped. It will be a black hole. Right? So if I know it's very heavy, I solve Einstein equations and I get this. Any question here? Okay. So now, now let's look at this system and analyze this metric a bit more carefully. So what is this metric? It's a function of R, and what happens when R is huge? Look, when R is huge, what happens to these functions f and g? They become 1. When R is huge, they just become 1 and I get 10-dimensional flat space. Does it make sense? Yeah, I go very far from the stack of branes, I don't see the stack of branes, I see flat space. Like when I have Schwarzschild, I go far away, I see flat space. Okay? So the first thing we see is that this metric goes, when R goes to infinity, to ds square of flat 10-dimensional flat space. Okay. Good. Now, on the other hand, you see that something also happens when R goes to 0. When R goes to 0, this function f, instead of going to 1, when R goes to 0, this function also simplifies and becomes, this becomes one becomes very small, 1 becomes very big, right? I can drop the 1. In one case I keep the 1, in the other case I drop the 1. Right? So there is another regime, R going to 0, which means that I am near where the branes were. Right? I'm near where the branes were at R equals 0. R equals infinity is far from the branes. R equals 0 is where they were. And there, when I go close to the brane, it's the opposite. Now, we drop the 1 in f of R. We just drop this 1 in f of R. And we get ds squared approximately equal to, let me try and hopefully it's correct, L squared will factor out. Let's see, so this will become R squared over L squared, right, when R is very small. And so G is the inverse of that. That is G. Okay. F is the inverse of that, so that will be L squared over R squared times the metric of 6 dimensions that I will write as dr squared plus R squared times the metric of a 5-dimensional sphere. I went to 6 dimensions and I wrote it in spherical coordinates. I wrote it as radial plus R squared times the metric of a 5-dimensional sphere. Plus, and now this part here, which is R squared, G is R squared over L squared Ah, perfect. Okay, great. You agree? I did, it's perfect. And so, this is equal to the following. I can say it's L squared times a metric of a 5-sphere plus another metric that I will call the metric of a space called ADS5, and this metric is whatever remains, so it's L squared over R squared dr squared plus R squared over L squared dx mu dx mu. Okay? And that's just a way of writing a space, and this space is called antecedent space. Okay? Now, so here it is just an observation that I forgot. Who was the square root? Was f or g? I forgot. G was the square root, right? And f was 1 over g. So this is square root of 1 plus L to the 4 over R to the 4. And this guy, this is the square root? This is the square root. So this is 1 over the square root. And we study this metric in two regimes. To infinity it becomes flat, and to 0 it becomes ADS5 times S5. Okay, that's just a true statement. Now, let's ask, what happens, what do I care about low energy? So I have this space-time with this metric, and I am an observer that I am the experimentalist. The same experimentalist that I was here. This is me. You see where I am. I'm far away from the brain, sending gravitons, like Arish was saying, or doing experiments, letting them interact with the brains, and then receiving them here. Right? So I have some experimentalists at infinity doing stuff with the brain. Right? And they see some low energy description. Now I want the same thing for those guys in that background. They are at infinity. What do they see at low energy? Right? So now, right. So what do we see at low energy here? And one thing we see at low energy is, very far away from the brain, we have gravitons. That's definitely part of what I see at low energy. This is just far from the brains. There are some gravitons flying around. That's what we saw. But now, let's point out something here. Let's see here, for the observer, for this observer, I have some time t. What is the time of this observer? This is t of the observer. What is this time measured by this observer? This time is x0. When the metric becomes flat, there is time here. That's the time that someone at infinity measures. Do you agree? Good. So that's x0. It's the time of the observer. Now, notice that ds squared, when I'm approaching r equal to 0, right? As I'm approaching r equal to 0, we see here that time comes multiplied with r over L. So the time for the observer in ADS5, right? The proper time for the observer there, right? So this dt for an observer there, which is square root of ds squared, right? The line element. is what? It's R over L times dt for the observer at infinity. You agree? A small time interval in ADS, a small invariant interval, is multiplied by R over L compared to a small time interval at infinity. Correct? And that means that the energies, the proper energies for an observer in ADS are the inverse, so I can put it here, times R over L are the energies seen by the observer at infinity. Right? Energies are the inverse of the times, and I just put it now on the other side. Right? So there is this huge redshift that if I am at R equal to 0, doing exploding nuclear bombs, from an observer at infinity, that's very low energy. Right? That is multiplied by R over L, where R is going to 0. So for an observer at infinity, what is low energy is supergravity plus anything that happens in ADS5. Anything in ADS5 is low energy. Whatever put here, you can put a black hole. It's multiplied by R over L, where R goes to 0. It's very low energy. Okay? And so here, you have anything in this ADS5 region. The full thing, all the degrees of freedom in your theory you can put there. Like I said, black holes, people, nuclear bombs, everything. So what's the theory? What's the fundamental theory then that you can put there in ADS5? Well, you put the full theory that you started with. So you put type 2b strings, closed strings. Closed because there are no d-branes anymore, it's just the background. But you can put anything, type 2b, closed strings, in ADS5 times S5. Just superstrings in ADS5 times S5. Type 2b is just the name for superstrings. You put everything there. Right? Everything there, because of this redshift, is low energy at infinity. Right? So you get, when is this description good? This description is good when the background is not changing much. That is good when this L is large. This L needs to be large. Otherwise, this is not a good metric, right? And L, I remind you, was proportional to G. So this is a good description when the curvatures are small, when L is big. It's a good description when G is big now instead of small. Which makes sense. I have a big, if the object is very heavy, it back reacts a lot on the geometry, then the background description is better than because there's a lot of back reaction. So this description is easier to work with when the coupling G is small, is big. This one is easier to work with when the coupling is small. But both would be true, that's the claim. And so we end up with the low energy description being either that box or this box. So we asked what's the low energy description, and we got two answers. This box on the one hand, and this box on the other hand. So what do? You come here, and now you equate both, and you cross. And you get a duality between type 2b strings in ADS5 and n equals 4 superannual. And that's ADS-CFT. Because it's string theory. I could replace 2b. It is just string theory. I have a background, which is a 10-dimensional background there. It's ADS5 times S5. Whatever you put there, it has some energy. And that energy is going to be low energy from infinity because of the huge redshift. This is the crucial factor. Because of this factor, anything at infinity that you want, that's low energy, you can put anything here. It's going to be low energy at infinity. Because I'm starting with string theory, right? So of course I have a fundamental theory of everything, that's string theory. In that theory I put either D3 branes, then I get low energy n equals 4, or I get 3, then I get the background, but I started with string theory, that was the rules of the game.
At that point where you put the L approximately proportional to G times N,
Yes.
why can't you just have N large and G when? Why is it important that G and not N?
Well, if you work out all the elements of the dictionary, you would see that N is related to G strings, G times N is related to G Newton. You would have to see, for some things N large is enough. To have really a good supergravity description, you need N large and G times N to be large as well. That would require going into more details than what I can go.
The other point is, I know that you crossed out this supergravity boxes, but what does it mean to have that should be plus supergravity?
So it really means that I have my background, and what we are saying is that the background, it has two regions. One region here, of size of order L, and that region is ADS. And then I have here this region, which is approximately flat. And here I have gravitons, and here I have anything I want. Now, here, we argued that I also have gravity, and here I have everything, and they are just decoupled. Right? They are just decoupled. Of course, you can couple it by just saying, I insert a bunch of probes that come from outside. But you do it by hand, right? If you don't put it, nothing will couple. There, you could ask, why don't these gravitons start interacting with ADS? Why doesn't stuff from ADS get out and go to the gravitons? Why are they decoupled? Right? And they are decoupled because ADS is a box. That would require going and studying, how do I see the geometry of this? What is this geometry look like? Because spheres, you know very well what's a sphere. I didn't tell you yet how to think of this geometry, but if you thought about this geometry, you would see it's a box. And because it's a box, when you put stuff inside, it cannot get out. So that's why the stuff inside doesn't go out. But why doesn't the stuff inside fall in? Why does that? And that's because they have different sizes. The stuff outside has a wavelength that is much bigger than the size of the box from the point of view of the outside. So it's like having an antenna that's not capable of capturing modes. If you cannot capture with a car antenna, you cannot capture some kiloparsec modes that are passing by. And that's why, from the point of view of the outside, these low energy modes, they have very big wavelength. And if you were to study the cross section for the modes outside to be absorbed by ADS, you would see that they vanish as the energy of the modes go to zero. So the cross section, not only they don't get out because ADS is the box, but they don't get in because ADS would be an antenna of a size that doesn't capture this long wavelength. And because it doesn't get out and doesn't get in, they are really decoupled, and what stays in ADS, what happens in ADS stays in ADS. And so we crossed them out, and we derived this powerful duality. So these arguments, this toy experiment of starting with something, taking a low energy limit, and then what we did is observe the decoupling of things. So that's why it's called the decoupling argument. And that's what the paper is about. It's about developing this decoupling argument, which I think is probably the most important idea in high energy of the last 50 years. It's this simple decoupling argument. That you have this system, which is A plus B, or C plus B, and you cross out B, and you get A equals C. And you could imagine developing in other cases. We started with D3s. Why don't we start with D4s, D5s, repeat the same games, and derive other dualities? And indeed, people did it, and there are other examples of other constructions. But you could then ask, oh, and now if I give you just a CFT, can you give me an ADS dual. That's much harder, of course. Because here we have the luxury of starting with string theory and deriving carefully something. Now if I tell you, deform type to B, put another string theory in ADS 5 times S5, or deform the S5 to something else, what do I do here? That's very hard. You can still use it as a toy model, but it's much harder to control. So, what time is it? 3:40? 2:40. So, I spoke for 1 hour. I have two options. One is stop here, I did the most important part, or we spend 15 minutes and we discuss a little bit of what's the geometry of this part that we call the ADS5, and we'll just discuss what's the geometry of this box. So I either stop here or say a few words about what is the geometry of this very simple metric. 4-dimensional Minkowski, R squared here, R squared there. I could, up to you. So I think we stopped in an important point with this derivation. Again, what we derived was n equals force per Young Mills is equal to type to B strings in ADS5 times S5. We derived that they are equal, but we also derived that it should be very hard to check, because this theory is easy to deal with at strong coupling, and the other one is easy to deal with at weak coupling. So we conjecture the duality, and it's awesome because it allows you to compute things that is easy in one theory when the other is hard and vice versa. That's great. On the other hand, it's terrible because we cannot check. Because when you compute something, you don't know what it would be in the other one. So you need to develop really powerful methods if you want to check, because you need to be able to do things either in field theory at strong coupling or in quantum gravity at very quantum gravity. And normally we don't know how to do it. But that's how EDS-CFT works, and that's why it generated so much activity, because it can be used as this powerful tool. Sorry.
Have you used the fact that you have the supersymmetry? The answers, or you need to have it?
It's only when you have supersymmetry that you know how to write, how to do string theory properly. And for example, string theory, when you don't have supersymmetry, doesn't have just massless modes and massive modes. It also has tachyons, for example, that we don't like. So if you want a theory of strings that starts with massless states, the easiest way is to do superstrings, for example. Now you could say, is that an obstacle? Can I just... yeah, good. Okay, let's ask the following. Suppose I take this gauge theory and deform it. I add some terms to the Lagrangian. What will happen? It will break supersymmetry. Right? That's how we break supersymmetry in all phenomenology. We start with supersymmetry, we add some terms that break supersymmetry, and we let the RG work, and we flow to something without supersymmetry. So there should be a way of starting with this duality and adding just add some term in the Lagrangian that breaks supersymmetry, and now this theory will flow to QCD or to pure glue. It will flow to a theory without supersymmetry. So if you learn what it means to add this term in string theory, to go to string theory, add a term and let it flow, then you will derive a duality without supersymmetry between n equals 0 Young Mills and some complicated background in string theory. The problem is that this looks like a detail, but it's very hard to do in practice, of adding deformations and letting it flow, because it's not a weakly coupled flow.
But then you not have the CFT.
It starts with a CFT, you deform, it's not a CFT, but then it flows to a CFT again. But it does not need to be a CFT for this to work. If I deform this theory and make it not a CFT, I would deform this theory and make the background not ADS. There is a connection between being CFT and being ADS, is that the symmetries of CFT are the isometries of ADS. If you break and you no longer have a CFT, you no longer have ADS. The background will be modified.
So, that side, it is clear by this redshift argument that you can put anything and just take the low energy and see that it's okay. But there, type 2B equals students, a lot of stuff, right? It's not. It's much more stuff than just was for sprinkles. So
That's right. So it's quite amazing.
Yeah.
It's quite amazing that this exists. Yeah.
So
Right, let's emphasize that. Here we are saying I have a theory with everything, including black holes and everything. This is a theory of quantum gravity. And it's in that dimensions. And we are saying it's equal to a theory without gravity in 4 dimensions. It's really, it's quite impressive. We have much more complicated, much more stuff here, including gravity, many more dimensions. And yet we say it's the same as a quantum computer basically, right? It's a theory without gravity, just a generalization of a pure glue. And they should be the same, so it's quite remarkable. It should be easy to disprove it if it was wrong, right? It's so crazy.
So from this argument, I didn't understand quite well why do you throw away these F4 terms when you look at the whole theory, not just the low energy? Because this is supposed to hold not only at low energy. It should.
Okay, so I think you are asking, can I do some duality at this level before dropping this one here?
Yeah.
Saying I have this full background, and the full background should be possible to describe with some theory that is no longer a CFT, but it contains all terms. But the problem is, at least one problem is that we don't know how to write all terms. So we would not have control over this theory. So we also don't know how to write a string theory in this background. We don't know how to write a worldsheet theory. So it would just be too complicated. But it's indeed a good point. Can we do better than this decoupling and not take such a low energy limit, but take and when it varies low energy but not so low, and we keep some information about the full background? Now the gravity and the box start interacting with each other, and here the brain starts interacting with the gravitons, and maybe we could do a little bit better than this. But this is already quite an amazing duality with a lot that we can explore. But
in principle,
in principle, people try to recover the one. That's how you would say in jargon. You would say, drop the one. How can we recover the one? That, if you talk to specialists, they would understand what you are saying. How can I go to the derivation and recover the one? They know what you are talking about.
Because of this E infinity equals E ADS times algorithm, you said you can put anything in ADS, but it's not quite right. Your parametrically high energy limits.
Right. So you can put, for example, stacks of D-branes and so on, but you would always put M of them, and M needs to be much smaller than N and stuff like this. So you always imagine some parametric limit where, but in practice you really.
Derivation would not work. We could then ask, what if we start from this side and derivations?
Yeah, you could imagine doing things on the gauge theory and on the string theory that would push this argument to the limit, yeah, and that could start breaking it, yeah. Yeah, that's true. Yeah. Yeah, what Arish is saying that there are some computations here that are much safer than others. If what you put in ADS is obviously a probe, a small object, it's much cleaner that this is going to work. If now you put an object inside ADS that's going to back react on ADS, can it also back react in a way that it's no longer a box and things start leaking out? There could be many more subtleties. So, yeah. But for example, you put a black hole in ADS. What do you find? You find that the metric is a box with a black hole in the middle. But it's still a box. Things don't leak out, right? Well, then I would say I'm allowed to put a black hole in ADS, for example. I had my box before, things were not leaking in because it was small. Now there's a black hole inside. Okay, they still don't leak in. And when I go inside, I still see it's a box, so I still don't leak out.
Yeah, I'm still confused on this.
Well, it needs to be a physical theory. So I start with the starting point here was type 2B strings. So here I start with a string theory called type 2B superstring theory. And in that string theory I put some D branes, and then I ask what's the low energy limit of this thought experiment.
Yeah, but where did you use, why is type 2B special here?
If I don't put type 2B but put some random string theory, I don't know what this supergravity is, I don't know what this low energy theory is, I don't know what the background is, I don't know what this supergravity is, I don't have any control. If you want to have control over what is the low energy degree of freedom of some theory, what are you going to do? Well, let me ask differently. What would you like to put instead of type 2B?
I don't know, maybe type 2A? Or you have
Type 2A, you don't have D3 branes in type 2A. What do you want to do instead?
So you mean,
If you want a string theory that has D3 branes, it's type 2B by definition. What do you want to do instead? Yeah, so the answer why type 2B is because that is what superstring theory is. Now if you say, I'll start with another theory of quantum gravity and put some extended object there and then do this game. Yeah, it could work as well. It is just that string theory is the only one that I know how to work, because it's the only one that I have control over low energy physics. But if there is another theory of quantum gravity and another thought experiment like this, where I get gravity plus something equal gravity plus something, I cross out gravity and I get a new duality. So it's a way of generating dualities, this decoupling type arguments. Now that you have the duality, you don't care about where it came from. Now you just use the duality.
So the fact that it's ADS file is relevant. If you change type 2B to some hypothetical string theory, it would change maybe details of chemical source dependence.
Right, so the fact that it's ADS5 is because it's a 4-dimensional CFT. The fact that it's S5 is because it has this 6-dimensional symmetry. So it more or less had to be that. But if you repeat this game, for example, when you put some M2 branes, which is another type of branes that exists, now they are 2-dimensional objects. Then you will get an ADS3 instead of an ADS4 instead of ADS5. And you will get a CP7 instead of an S5. And that will be another duality that exists, which is called ABJM, where you have a 3-dimensional Chern-Simons matter theory with n equals 6 supersymmetry is equal to type 2A, there 2A, like Deshwan was asking, in ADS 4 times CP3. CP3, I said CP7, CP3. So, yeah, that's it.
There was a puzzle.
Ah, there was a puzzle. Indeed. Good. So now we have this puzzle. Right? The puzzle was, okay. So let's try to erase a few things and discuss just that puzzle finally. So, okay, do you have energy to go for a little bit more and we discuss the puzzle and a little bit of jump? Okay, so this is the metric that we got. So we got, let's erase everything that we don't need. So we got type 2B strings, supergravity we crossed out, but we keep type 2B strings.
That's just one more.
Of course, yeah.
You said that you can add gravity to ADS5, but you crossed supergravity. How?
Yeah, that was the supergravity far away from the branes. Those gravitons I crossed out. Now I have the gravitons close to in the ADS5 region. Those I keep. They are separate. It would be like gravity in the solar system versus gravity at parsec scale. There they don't decouple. They are coupled to each other. But here, because ADS is like a box, I have gravity inside the box and gravity outside the box. So they would... But inside the box, I don't drop inside the box, I don't drop massive string states. I keep everything. All the massive string states. I can have massive particles inside ADS. I keep them. Right? So now I could have ADS and describe massive particles interacting. 3 massive particles, for example, interacting in ADS. Right? So I would keep them. I would not drop them even if they are massive. Okay. So let's keep this picture to remind ourselves where this came from. Oh, here I erased already, but okay. Okay, so now here is the puzzle. N equals 4 super young meals is some large N theory, like this one up here. And so in this large N theory, if I consider some quark-antiquark potential, and I sum it all these diagrams between this quark and antiquark, in technical terms this would be computing a Wilson loop, but if you don't know about it, don't worry, it's just a quark-antiquark. I compute this and it looks like a flux tube. So this would be summing all these gluons in N equals 4 super young meals, and it would look like it should be some kind of flux tube string that is discretized and moving here. But on the other hand, we said that no, it's a CFT, so it should be rather some delocalized Faraday lines, and the potential should be just alpha over R. Because there's no scale, it's a conformal theory, so it needs to be just Coulomb force. It's the only thing possible. And it's true, the result is alpha over R. It's correct. Mathematical, it's alpha over R. And so the tension is, how can these two be true? Okay? Okay. And these things, these lines here, are the end points of one of the strings, and this is the end point of the other string. Right? So this is a string end point. Now let's look at ADS. ADS is written here, and you see that ADS, let me change variables and let me define Z to be L squared over R. Then the metric becomes L squared, or L over R. Then the metric becomes L squared times dz squared plus dx mu over z squared. Okay. So this way of writing is nice because, is it correct what I wrote or not? Not really. R as units, it should be correct. Is it correct?
Correct up to some definition.
Yeah, it's not correct, right? Yeah, now it's correct. Okay. And so, this is the metric. So this is what we call ADS. And let's see how geometrically you can think of this metric. You see that whenever z is constant, I get flat space rescaled by 1 over z squared. So different constant z's give different flat spaces just rescaled. So one way of thinking of this metric is that I have different copies of Minkowski space, a 4-dimensional Minkowski space. And as z increases, these copies become smaller and smaller as z increases. And here it's z equals z. Okay? Z equals 0, you see, it's the boundary of this space. It's when this matrix is exploding. So the matrix becomes bigger and bigger and bigger. Z equals 0 is the boundary of this space. So this Z equals 0 is equal to the boundary of ADS, which before this was R equal to infinity, which makes sense, right? It's when we are leaving ADS. We are going towards the end. Okay? So Z equals 0 is the boundary of ADS. Right? So that's where we have this ADS, and this is the boundary. And now the idea is that we have this four-dimensional object. That's our boundary. This is the boundary of the space. And that's where you should think that n equals 4 super m nil lives. Why? Because what did you do in the stack of D brain picture to interact with the stack of brains? You went to the table and you send stuff from infinity here, right? You don't go and start sending stuff inside your sample with your dirty hands, right? That will disturb everything. That's not how you do things. You send stuff from infinity carefully, not to disturb what's going on. So your probes and so on come from infinity, not to touch the table. So this, the boundary of ADS, would be where n equals 4 lives. And now on this boundary, let's draw the quark and the anti-quark. Right? That was the quark and the anti-quark endpoints. I just redrew the quark and the anti-quark as these lines. And now there is a string that goes between this quark and the anti-quark. Now you see that the string has huge length when z is very small, because there is a 1 over z squared. So if you want to minimize the length of the string that is stretched, because that will have the lowest energy when it has the minimal length, you want to avoid connecting them close to the boundary. That costs lots of length. Do you agree? So what you want to do is to do something like this, where the string that connects the quark and the anti-quark goes inside. Right? That's the string connecting the quark and the anti-quark. Right? The string likes to minimize the length. Right? It's like soap bubble. Right? I pick some soap bubble and it likes to have the minimal length. The surface there is a huge gravitational wind, if you want, which is this 1 over z squared. And so it sends it inside. And so this is the picture we should have. We have a string that is going inside. And then, if we ask, I only live at the boundary. What do I see? You see the shadow of this string that is inside. And so what do you see? You see some kind of shadow of this string. Because you are in the boundary. And that's the fat Faraday lines. Is the image of this string that is inside. So what's the resolution to this tension? Is that this picture does tell you you have a string. So this is correct. This picture is correct, it's Faraday. What this picture doesn't tell you is that this string needs to be in 4 dimensions. That was your extrapolation. No one told us that the string that this is describing is in the same dimension as the theory. And it's not. This picture is correct, but you should draw it like this, going in some holographic direction z. And this is compatible with this, because what you see is like the shadow of this holographic direction. So imagine things are not propagating here in the blackboard like this, but they are propagating, doing a circle like this from here. Then the effect on the blackboard spreads out, right? If I have some particle going from here to here, the net effect on the blackboard gets fatter because it's going more and more and more inside. Right? And if you separate the points, it goes more inside, so the Faraday lines open more. That's exactly what we get, what our intuition tells.
But when we compute, it is 1 over r.
Yeah. So that would geometrically come about correctly. If you do the computation, indeed, what would happen is that the length of this curve, the length of this curve would be, or if you want, yeah, the length of this curve would be proportional to 1 over r, where r is the separation between the quark and the antiquark.
How precisely is this shadow works? How
No, this is at the level of a cartoon. Now if you ask, can I use ADS-CFT to rigorously compute this quark-antiquark potential as a string here and get 1 over r? And the answer is yes. That was the paper that Aldesiano wrote 1 year after ADS-CFT, showing that the quark-antiquark potential gives 1 over r. But this is a cartoon, it's true, but I just want to show that at the level of the cartoon there is no tension. Now whether it is working precisely with the right numbers, I need to do a computation. I could do, but that would be a detail. So let me conclude saying, so we saw that ADS is a sequence of a flat space. It's a sequence of a flat space. There is another way of writing ADS, which is that ADS, the very same ADS, is equal to an hyperboloid. And this hyperboloid, if I have ADS 5, this would be an hyperboloid inside 6-dimensional space, R2, 4, which would be a space with 6 dimensions. And in the same way that if I put a sphere in 6 dimensions, I get a 5 sphere. An hyperboloid in 6 dimensions gives a metric that gives a space with 5 dimensions, because it's one constraint in 6 dimensions. And it's possible to show that this metric is nothing but the metric of this hyperboloid. And then the boundary of this hyperboloid, which is this line here if you want, where when you go to infinity, is the same as the boundary of this space, which is this 4-dimensional part. Okay? So there exists such a description where you describe a point in ADS not as a set Z and then some small x. That is a way of describing a point in ADS. There is another way of describing a point in ADS, which is you give me a 6-dimensional vector. Instead of 5 variables, you give me a 6-dimensional vector, but the 6-dimensional vector is constrained to be in some hyperbola. In the same way as a sphere, you can give me a bunch of angles, or you can give me a point in a vector in one higher dimension, except that it is constrained so that x squared is 1. Okay? So here as well, you can give me a 6-dimensional vector in this hyperboloid, or you can give me a 5-dimensional set of unconstrained variables, and it is the same thing. And that's another way of thinking of ADS. So ADS is an hyperboloid like this. And then a boundary point here was a 4-dimensional set of variables. And here, a point in the boundary would be the boundary of this hyperboloid that you could describe as where does the hyperboloid asymptote to. And the hyperboloid asymptotes to a light cone. If you imagine that you have an hyperboloid and you go, it becomes closer and closer to a light cone. So you can describe the boundary of this space. It's the same as the boundary of a light cone. And so you can describe points in the boundary as light rays. But light rays are also 6-dimensional objects. You just specify in which directions they go. And that gives you a nice unified description where the point in the boundary, you can also describe it as a point in 6 dimensions, except it's a light ray in 6 dimensions. And then you have this beautiful description, very geometric, of ADS, where ADS are 6-dimensional points that are in a hyperboloid. Boundary of ADS are 6-dimensional light rays. Because light rays are asymptote the same thing. That's a beautiful description that people call the embedding description. And this would be embedding variables, and they are very convenient to do computations. And we are going to see it on Friday. Some computations in ADS. Where you have ADS, that, as I said, it's a box. To see it's a box, I would write it in yet a third set of variables that would make manifest that it's really a box, and I'm not going to do it. I'm just going to draw a cartoon to conclude that we can think of ADS as a box. Saying that something is a box means something concrete. Means that if you are here and you throw a rock, the rock comes back. That's what it means you are in a box. You throw something and it comes back. Right? So that's what it means. So we are in this box, and now there are points at the boundary of the box. So that's the boundary of ADS, which is 4 dimensions, and they are parameterized by a 6-dimensional light ray. We have a point in the middle of ADS that's parameterized by a 6-dimensional vector. And now we could ask, how do I do computations in ADS? Sending stuff from the boundary of ADS. That could be like the gravitons that we send. They are at the boundary of the box when I'm looking at a table and from infinity sending stuff. And letting them interact, like doing some kind of Feynman diagrams where things would come from the boundary and interact. So how do I start with 3 fixed points at the boundary, 1 point that happens in the bulk, and how do I do this type of, how do I measure this type of interactions? And this would give me some kind of 3-point interaction, for example. Okay? And I'm just setting the stage for some computations that we'll see on Friday. That will be an example, but we will see in more detail. This will be reviewed again in more detail next Friday. So yeah, so EDS and this, the translation between these variables and these variables. How would you show that this is equal to this? The same way, how do you show that a sphere is equal to something that you write? You just parameterize this hyperboloid in an explicit way, plug it into the flat metric, and you see that you get this. So that's done in Appendix 7 of the paper. If you reach the appendix, which somehow I doubt, you will see that in the last appendix of the paper, he plugs the parameterization of this hyperboloid and shows that the hyperboloid gives it. Okay? So now if you want to see this in detail, now that you've got the background better, you can check that appendix. That step of going from this to this is very well explained in the paper. Okay, good. Last section.
Connect with Hari's question. You said that we keep all massive modes of the string in it. Yes. What if you consider like a very, very heavy string state, like which pulls with n? How can we be sure that it doesn't leak out?
I would say that if you put something very heavy in ADS, and if the metric is back reacted and changes the asymptotic form of the metric at infinity, you should not trust it. But if the asymptotic, the metric is still ADS, you trust it. I think this is probably fair, right? Because if it doesn't touch infinity, it's still a box. Then it's fine. But if you put something so hot that melts the box, then the box approximation, you destroy the box. So, and it's exactly the same. Any other questions? So on Friday we meet at 10, probably here because there's a conference. It seems upstairs. So let's meet here at 10 from the last 4 presentations. Very good.
about